We talked about the structure and the hydrogen bonding of alcohol, and due to hydrogen bonding, there is a high boiling point, unusual high boiling point for alcohol compared to alkanes and other hydrocarbons. And we talked about nomenclature. We have an example here for phenol nomenclature, which is aromatic alcohol. Aromatic alcohol means that you do have a benzene ring that carries the OH or the alcohol functional group, and the parent name for benzene ring attached to OH or carrying OH is called phenol. That's the parent name. Also, the carbon that carries the OH is numbered as carbon 1, and you start numbering in a way that a smaller number would be assigned to other branches if there is any branch. So if you go clockwise from carbon 1 to 3, you get 3 chlorophenol. A 1,3 position on a benzene ring is also known as meta. So if you have a 1,3, that is same thing as meta. Okay. Basically, when you say meta, that means that chlorine is on position 3 with respect to OH is on carbon 1 or position 1. Another example, you have again phenol, and there's a methyl group on the benzene ring. The methyl group is with respect to the carbon that carries the OH is on carbon number 4. And if you do have a 1,4 position, that also means that it's para, or that's another name for it. A 1,2 is ortho. So we have the ortho, meta, or para position. So ortho.
So that's if they're across from each other, right?
Para means that is across from each other. Okay, that's para. Ortho, it looks like 1,2. So if you have like a OH on carbon 1, and then let's say if you have a Br on carbon 2, in this case, this is a ortho. Okay, orthobromophenol. Phenol. So we have 1,2 for ortho, and meta is 1,3. Para would be 1,4 with respect to each other. Okay, any questions?
That works for all rings or just benzene rings?
Benzene ring.
Okay.
That's only for aromatic, yes, aromatic compounds or benzene ring. So OH is a high priority functional group, so it must be part of the main carbon chain, even though it's going to compromise the longest carbon chain. So if you go from here, carbon 1, 2, 3, 4, and 5, it's not going to include, it's not going to have the 7 carbon or 6 carbon that you could have if you go for a straight, but if you go straight, there is no OH. So you must include the OH. So the rules kind of, we always talked about longest carbon chain until we start with the alkene. And we said that longest carbon chain, including alkene functional group. And now is longest carbon chain, including the OH functional group. So OH functional group must be part of the ring. Any group that did not take number is going to be named as a branch, and the branch that we have here, isopropyl, and this branch is a iodomethyl. So iodomethyl. Then you have to just put them in order with the alphabetic order. Branches with alphabetic order. If you have the iso, I would count. This is the only prefix that would count. Like if you have di, D doesn't count. Like for dimethyl, D doesn't count, M counts. But for isopropyl, I would count. And the name is already here. Okay. For the physical property, we talked about hydrogen bonding, that alcohol would have hydrogen bonding, and because of the hydrogen bonding, the boiling point is higher or unexpectedly higher compared to other hydrocarbons or compounds that they have similar molar mass. The molar mass is 46, molar mass 46 for ethanol and dimethyl ether, and then you have this is like 44 for propane. But the type of intermolecular forces that you have for dimethyl ether is dipole-dipole interaction, because it's a polar molecule because of the polar bond that you have and pairs of unshared electron on the oxygen. But alcohol, besides being polar, also specifically has hydrogen bonding, and because of hydrogen bonding is the strongest among for the molecular compound, the strongest intermolecular forces. So the boiling point is going to be much higher, 78 compared to minus 25. And for propane is only dispersion forces. There's no polarity here. And for dispersion forces, because they are very weak, the boiling point is going to be even smaller. Any questions? Questions? No questions. Okay. Solubility of the alcohol, these molecules, they are up to 4 carbon, they are soluble in water. So when you say solubility, basically solubility in water, unless you specify the solvent. Up to 4 carbon, it's soluble, and after that, the solubility is going to decrease. So for pentyl with 5 carbon, it's only 2.7% soluble. So after any number higher than 4 carbon is going to be significantly low solubility. You do have the OH bond, so its solubility is not 0, but it's very low. And the reason for that is when you have the alcohol with 4 carbon in the main carbon chain, this is long enough to still be polar molecule. So you do have a polar head and you have a non-polar tail. Now, if you increase if you lower this number of carbon and the non-polar tail to 3 carbon, then the priority goes to OH, which is a polar molecule. So the effect of the polarity or the hydrogen bonding is going to be more significant than the non-polar tail. But if you add another CH3 here, another carbon, then the molecule is going to act like a non-polar, and it only dissolves by 2.7%. So the cutoff is 4 carbon. So less than 5 carbon is going to be soluble. More than 5 carbon, even though it's a polar molecule, is not going to be soluble because of the long carbon chain that you have. Alcohols, the commercially important alcohols, or the first and second member of this family. Methanol is also known as the wood alcohol. It's very toxic. The toxic dose is like 100 milliliter. What does it mean? That it can cause blindness, it can cause coma, it can cause death if it's ingested about 100 milliliter at once. It can cause death, actually. And for ethanol is the only edible alcohol. So ethanol can be prepared from fermentation of the sugar and starch in grains. So it depends on the source of the fermentation. You get different taste and different name for the alcohol, but is the only edible alcohol. In industry also, it can be prepared by hydration of ethylene or ethene to carbon alkene. You just add water. That would be industrial. Because if you try to use sugar or grain, it's going to be very expensive to get the ethanol. 90 the lethal dosage for this, or toxic dose, is like 200 milliliter. Even though it's edible, it doesn't mean that you can have as much as you want. It's like if you have 200 milliliter at once, it can cause death. And that's like a LD50. LD50 is like the for 50% of the population. Like if you give 100 people the same amount or 200 milliliter of the ethanol, 50 of them would show like a reaction right away. So the statistics, it doesn't apply to everybody. So, some people, they would have lower tolerance. That could be 150 or 100 milliliter even. But this is the average number. The high octane rating, and you also have the gasohol, 10% ethanol in gasoline. Basically, combustibility of the gasoline would be increased, and then the mile per gallon is going to be more efficient. So it would be higher mile per gallon of the gasoline. That's what that's why they are adding some ethanol or methanol to the gasoline. Okay. So methanol and then ethanol, then you have propanol, or isopropyl alcohol. With the isopropyl alcohol is called also as a rubbing alcohol. And that's what you actually find in the brown bottles, and they sell it, and they use like it's toxic. It's highly toxic. You don't want to ingest it. And during pandemic, I don't know, how many of you read the bottles, the label for the bottles. Some of them, they were those hand sanitizer. They were made with ethanol. Others, they were made with methanol, and then some were made with the propanol or isopropanol. The safest one were the ones that they were made with the ethanol, because if it's like no wash, you just apply the gel and then you eat. You don't want to ingest methanol or ethanol. And at that point, I guess it was just a choice. Which one should they choose to stay alive? Acidity of the alcohol. Are alcohol acidic? Are they acidic or not? Is alcohol acidic or not?
No.
Okay, very good. Because if it's acidic, you won't be able to drink it, right? You do have one of the alcohol that is like edible alcohol. So it's not acidic. The pKa, like a 15.5, very close to pKa of the of water. The only alcohol that is more acidic is the phenol. Phenol is more acidic than than other alcohols. So if you have aromatic alcohol, is acidic, but that's not edible anyway. Acidity even decreases as the number of the carbon increases. So it can go from, pKa of 15.5 to 16 and 17. Phenol is the one that is more acidic, and that it says 100 million times. So pKa is going to be about 10 to 10. So you have 10 versus 15 or 16. So 100 million times more acidic than the alcohol. And let me see what we have here. So if you have a very weak acid and you try to remove the hydrogen, the base that you are using, it must be super strong base. So you cannot use the ethanol and add sodium hydroxide in order to remove the hydrogen because it's not going to work. It's not strong enough. Why do you need very strong base? Because the acid that you are using is very weak acid. So in order to remove hydrogen from alcohol, you must use sodium or potassium that can actually replace the hydrogen. It can remove the hydrogen and changes to alkoxide. But since the phenol is a stronger acid, for phenol, if you want to change it to phenoxide, you can actually use NaOH. NaOH is strong enough to remove hydrogen from phenol, but is not strong enough to remove hydrogen from cyclohexanol. Cyclohexanol is very weak acid, so you must use sodium or potassium to remove that hydrogen.
Professor, those are the only elements or molecules that can we use in order for us to remove the alcohol, or there are other ones? Like, can we only use...
These are the only ones that they are strong enough to remove the hydrogen from the alcohol, sodium or potassium.
Okay, thank you.
You're welcome. But for phenol, you can use sodium hydroxide. Sodium hydroxide is a strong base, but it's not as strong as sodium or potassium itself. Okay, any questions? And the reason why phenol is stronger acid is because when you remove the hydrogen, if you go back to chapter 1 and 2, acidity, the factors that one of the factors from Oreo that would actually affect the acidity of the compound is formation of the resonance on the conjugate base. The conjugate base from phenol, it can form 4 different resonances. And because it can form 4 different resonances, that's the fact that is going to make the phenol more acidic, because after removing the hydrogen, it's going to be stable on its own. How is it stable? It's like stabilized by formation of different resonances. So the negative charge on the oxygen can be delocalized, it can move, and is because it's conjugate to a double bond. And when it moves to this carbon, it's conjugated to another double bond. So it's separated only by one single bond from a double bond. So the pair of electron can drop in, the pi bond can move to the next carbon, and the negative charge would be on the next carbon. So you can see that there are 4 different resonances for phenol. The more resonances, the more stable conjugate base, and the more stable conjugate base, that means that hydrogen can be removed easier, because what is left is going to be stable. Okay, so we talked about nomenclature and some properties, physical properties and acidity of the alcohol. Now, preparation of the alcohol, how would you prepare? It would be preparation of alcohol, and I think we already discussed that reactions of alcohol would be covered in organic 2 class. So preparation of the alcohol, one method was hydration of alkene. If you remember from chapter 8, which you have to remember for your exam next class, or next week rather, your 3 methods of hydration. One was direct hydration. That means water was added, acidic water was added to alkene. So hydration of alkenes, acidic water in acid solution, it can be added to alkene. The product was a mixture of, it could be the product is Markovnikov product. There's a chance for rearrangement. And also, we can't say it's a syn addition or anti-addition because you get sp2 hybrid intermediate. Carbocation intermediate is sp2, is planar, so it can go either way. Oxymercuration, demercuration, this is indirect addition of water. Indirect addition of water using oxymercuration, demercuration reagent. The product was Markovnikov product, and the addition was an anti-addition, meaning that hydrogen was added from different side than the OH. And there's no rearrangement. A triangle was formed as in the intermediate, if you remember. Hydroboration, oxidation, anti-Markovnikov, addition of water. So the net result is addition of water, which is adding H and OH. H to one carbon, OH to another carbon. So if it's Markovnikov addition, hydrogen will add to the carbon with a greater number of hydrogen, or rich gets richer. If it's anti-Markovnikov, hydrogen will add to carbon that has least number of hydrogens. In hydroboration oxidation, the addition is a syn addition. That means if you have CC double bond, hydrogen will add from the same side that OH is going to add. For vicinal diols, you start with the alkene, and you had two methods to do that: cold dilute permanganate. If you use cold dilute permanganate, it's going to give you vicinal diol. You could do osmium tetraoxide. That would also give you a vicinal diol. And then hydroxylation of the alkenes, which you would first make the epoxide and then add water. And when you add water, it's going to give you OH and OH. Osmium tetraoxide and carbon and the permanganate syn addition, and this one is going to be anti-addition. Added from the same side or added from opposite side. But for all three of them, two OHs is added, one to each carbon carrying the double bond. Using of organometallic reagent for synthesizing of alcohols. First of all, what is organometallic? Organic chemistry is based on carbon and its compounds. So there wasn't supposed to be so you basically find carbon, hydrogen, you find sometimes oxygen, sometimes sulfur or phosphorus and nitrogen. Organic compounds, they are not very popular using of any metal. So if you bring a metal and add to organic compound, you give that new name and you say organometallic compound. Organometallic compound, if you have a metal attached to carbon, then definitely metal is going to be positive charge. As a result, the carbon is going to be negative charge. So if you have carbon attached to lithium, or if you have carbon attached to magnesium, MgBr, Mg or MgCl, because magnesium has to have two bonds. One is attached to carbon, the other one is attached to another halide. Magnesium is going to be positive, definitely. Between carbon and magnesium, metal, non-metal, definitely magnesium would be positive, and this would be negative. So organometallic compounds, they do have carbon attached to a metal. What's unique about that is that carbon is going to be negatively charged. And if it's negatively charged, is it going to act as electrophile or nucleophile? because is negatively charged, has extra electron, is looking for positive center, so it is a nucleophile. And because it's a negative charge, actually, it's not just a pair of unshared electron, it's going to be a strong nucleophile. Same thing here. This is like a strong nucleophile that you have. If you have a nucleophile can attack a partially positive carbon. Where can you find partially positive carbon? You can find it in CX. So if you have carbon, an alkyl halide, basically, example of that would be CBr. So if you bring the organometallic compound to this, because it's partially positive, partially negative, the nucleophile is going to come in and the leaving group is going to leave. So you get substitution type reaction. Another compound that you could have partially positive carbon is the compound that they carry CO double bond. CO double bond can be like formaldehyde. You can find CO double bond in aldehyde. So you have R and then H. That's aldehyde functional group. When you say R could be carbon or carbon chain. So it could be 1 carbon, 2 carbon, or 3 carbon alkyl group. So R represents alkyl group. Or you could find that in ketone. So when you have ketone, you have 2 alkyl group attached to one carbon. To either one of these are nucleophile from organometallic compound can attack, and then when it does attack, if you look at the mechanism of the reaction, which is going to be covered later, but I was just going to talk about the carbon with the positive charge or slightly positive charge or partially positive carbon, because hydrogen, oxygen is partially negative. This is going to be partially positive, partially negative, partially positive. And same thing here when you have alkyl halide. The other type of nucleophile, other than the alkyl lithium and Grignard reagent, you could have the acetylide ion. Acetylide ion, which is coming from terminal alkyne. From terminal alkyne, we saw this in chapter 9 already. You add sodium amide, it would remove hydrogen. And sodium is going to replace it. Now you have carbon attached to sodium. So this is going to be plus and carbon is going to be negative. And because it's negative, it's acting as a nucleophile. So this can also attack the partially positive carbon from alkyl halide or from carbonyl compound, any carbonyl compound. And the examples of carbonyl compounds, you could have formaldehyde, you could have aldehyde, or you could have ketone. One rule you need to know by heart is that when nucleophile attacks a carbon, so if nucleophile comes and attacks this carbon, you have to look at the compound that you have, the compound that contains that carbon with partially positive charge. Is that carbon attached to good leaving group, or is there a leaving group to leave? If there is a leaving group to leave, what's going to happen here? Let's say you bring the acetylide ion, and then this carbon. Can you tell me how many bonds this carbon already has? I'm talking about this carbon with the blue arrow on it. How many carbon does it have already?
How many what again?
4 bonds already, right? How many bonds? Yes, there are 4 bonds. 1 is to X, 2 is to hydrogen, and 1 is to R. What's the maximum number of bonds a carbon can carry?
4.
4. So if acetylide ion comes and forms bond with this carbon because it has partial positive charge, and then this is negative charge, a negative positive charge, they attract each other, a new bond would form, is going to put this carbon at the risk of having 5 bonds, which is going to make this carbon very unstable. So what would be the solution? The solution is a weakest bond has to break. What is the weakest bond here?
So wouldn't it be X?
The X, because X is a good leaving group, the X is halide and halides are good leaving group. So the leaving group is going to leave. And when the leaving group leaves, then your molecule is going to be stable. What happened here, there's increase in carbon chain. You brought 2 carbon plus R from acetylide ion, and you brought a CH2 plus R from your alkyl halide. So the carbon chain has increased. So that's one case. When nucleophile comes and attacks partially positive carbon, if there is a leaving group, the leaving group must leave, because if it does not leave, then that carbon is going to have 5 bonds, and that is not stable. It's very unstable.
So normally that X is like a representation of like iodine, bromine, one of those, right?
Yes.
Okay.
Yes, right. And as a result, we have increase in number of carbon in the carbon chain. Now, the other case, another case that we are going to look into is when you have a carbonyl group. Carbonyl group already has 2 bonds to oxygen. So there are only 2 other positions that they can be occupied by alkyl group, or it can be occupied by hydrogen. Now, R or alkyl group, I'm going to say R group, is not a leaving group. I'm not even say good leaving group, is not, okay? It's not leaving group. Hydrogen also is not, hydrogen is not leaving group.
Is it because R in this situation is a metallic, right?
No, R is not metallic. R is just the alkyl group.
Okay.
R is alkyl group. R could be like a CH3. Okay. R could be CH3. R could be CH3, CH2. R could be any alkyl group.
Okay, so typically a leading group is really just like the halogens, really.
It's not just halogen. Like OH is a leaving group, but it's not a good leaving group.
Okay.
But hydrogen is not leaving group at all. It's not going to leave. It's not a good leaving group, because if it leaves, doesn't know what to do. So R, like if you, I think if any of you remember when we were talking about the leaving group, I used the example of a teenage, a teenager versus like adult child that is, it can go, it can be stable on its own. So it's a better leaving group. If you remember that example, that a teenager is not a good leaving group because it's not going to be stable on his own when it leaves the house. If you use that example, then hydrogen is like an infant. Can infant leave? It's not even an option. It's not a leaving group. Same thing for the R. If you make the alkyl group leave, is not going to be stable on its own. So it's not leaving group. Okay, so with that, I'm going to clear this slide so I can write more. Here, when the acetylide ion is coming and forming bond with carbonyl group, is there a leaving group here attached to the carbon?
I mean, there is, but it's not a strong leading group, right?
Which
there's
one?
No leaving group.
There is no
The
leaving
oxygen.
group.
Oh,
Okay, I should have added to my list that oxygen, hydrogen, and R not leaving group. That's oxygen is different from OH. Okay, these are separate. So it's not, there is no leaving group. So when nucleophile or strong nucleophile comes in and attacks this positively charged carbon, then from carbonyl group, because there is no leaving group, the pi bond is going to break over the oxygen. So we have one bond has to break, because this carbon already has 4 bonds, right? Can you count 4? Do you see 4? 2 of them are attached to oxygen and 2 attached to R group. So total of 4 bonds for this carbon, and that's the maximum. When you bring this new bond, it's going to make this carbon go through very unstable situation of like having 5 bonds. And then there has to be a solution. The weakest bond has to break. What's the weakest bond that you could see there? There is no leaving group. The weakest bond, when you talk about the CO double bond, you have 1 sigma bond and you have 1 pi bond. So pi is a weaker bond, right? The pi bond is a weaker bond. So pi bond is going to break. What is pi bond? It's just pair of electrons. It's going to break over the oxygen. Now,
so in a sense, it's just rearranging itself, kind of.
The pi bond breaks over the oxygen, yes. So you have alkoxide now, because oxygen is a oxide, now is an ion. Then you need to protonate that. It has to gain a hydrogen and it changes to alcohol. So if you bring a nucleophile of either acetylide ion or Grignard reagent or the alkyl lithium, it can attack the carbonyl group. And when it attacks the carbonyl group, there is no, from formaldehyde, from aldehyde or ketone, there is no leaving group. And since there's no leaving group, the pi bond will break over the oxygen. It forms alkoxide. You protonate the alkoxide, you end up with alcohol. So this is one method of preparation of alcohol. Now, you don't like this pi bonds, you don't want to have triple bond. What would you do if you don't want to have the triple bond there? How would you get rid of the triple bond? You make it single bond.
You would probably break those bonds. So instead of adding the H3O beforehand in the what is it, alkoxide, you would probably put like a leaving group so it'd break one of the 2 pi bonds on the carbon. Would that be right?
No, after you're done with the preparation of the alcohol, then you can saturate it. You can add hydrogenate it. You could add H2 with the catalyst, and it will change to RCCOH. Okay, you hydrogenate. If you don't want to have the triple bond, you would hydrogenate. Add hydrogens. Okay. So we looked at the acetylide ion. Now we want to look at a Grignard as another organometallic reagent. In a Grignard reagent, you have to prepare the Grignard reagent. How would you prepare Grignard reagent in the reaction mixture? You start with alkyl halide and add magnesium. Solvent is going to be ether, and alkyl halide with the magnesium. If you reflux it, you boil it basically for 30 minutes. Magnesium would be inserted between carbon and the iodine or halogens in general, and you end up with Grignard reagent. The general formula for Grignard reagent is RMgX. X is halide. This could be chlorine, bromine, iodine. R is the alkyl group. And Mg is Mg. It's magnesium. So that's the general formula for Grignard reagent. Okay. So Grignard reagent, that's the general formula. So you start with the alkyl halide, which is the Rx. R is alkyl. I have to say this often. Alkyl because you know that R is alkyl in chapter 3, but by the time it comes to chapter 11 and 12, then you forget that R is alkyl. So alkyl group, and this is halide, could be chlorine, bromine, or iodine. Okay, we don't work with fluorine because it's very, reactive, is not for the lab synthesis special. Now, with the alkyl group here, mixing with the magnesium, you insert the magnesium in between, but anyhow is going to form bond with the carbon. So magnesium is going to be positive and carbon is going to be negative. So you have your nucleophile now. This, as a strong nucleophile, can attack a carbonyl group. Okay, this can attack carbonyl group. So these are some of the examples of the Grignard reagent. Can you look at them and see how versatile it is? You can have like open chain alkyl, you could have a cyclic alkyl, you could have a vinyl group. Okay, this is like a allylic halide, and then you could have phenyl bromide, that's like a aryl halide or aromatic halide. So any of these can give you Grignard. So that's a good thing about using Grignard, because you can make Grignard from primary, you can make Grignard from secondary alkyl halide, you can make Grignard from benzene ring, you could make it from cyclic alkyl, or from the allyl group also. So you have allyl or aryl, which is the aromatic. So any of these can give you Grignard, which is one piece of the reaction that we are going to concentrate on, addition of the organometallic compound. Okay, you need your Grignard. How to prepare it? Make sure that you have a carbon attached to one of the halogens, and then mix it with magnesium, heat it up, and you get your Grignard reaction. So you have your RMgX. So you have the R with the negative charge, and then your Mg is a plus charge. Mg usually has like 2 plus charge, but chlorine, because it's negative, or halide is negative, you have 2 negative and 2 plus charge there. So the ether that you are using is just the solvent, is going to stabilize the substance, but is not reacting. Okay, in the reaction, it's not part of the reaction. So any halide can be used to prepare Grignard reactions. Any questions?
So the only requirements for producing a Grignard substance or whatever was magnesium and heat, right?
Yes. And then on the other side, your reactant must have a halide.
Gotcha.
It must have a halide. You also have another reagent, is called the organolithium reagents. The organolithium reagents, very similarly to Grignard reagent. In this case, you use lithium instead of the magnesium with alkyl halides, with halides in general. With halides, you would use lithium and you would get organolithium. In this case, you don't have RMgX, instead you have RLI. So it's the alkyl Li. Li is positive, alkyl is negative. So basically you get pair of electrons on the carbon that attaches to the Li. And how do you do this? This way, Li is going to replace the X is not inserted. You don't have like a R. You don't have RLIX. It's just the RLI. So it replaces the X. You can use any type of halide also to mix it with the lithium, and you would get the alkyl lithium, okay, the organolithium reagent. When you have your organometallic reagent, it could be from Grignard reaction, which we looked at the Grignard reaction, and it was R negative MgX. So we are only concerned about this part, or from RLI. Okay, so the R part, organometallic reagent, it can attack the Grignard, it can attack the carbonyl compound. And since carbon from the carbonyl compound already has 4 bonds, the pi bond is going to break. So you get alkoxide, and it should follow up by hydrolysis, but you have to add water. And in presence of the acid, you would say either H2O or H3O plus. You protonate the alkoxide, and you end up with alcohol. So this is a major preparation for alcohol. You can make primary alcohol, you could make secondary alcohol, and you can make tertiary alcohol with this. So if what you need to memorize and make sure to write down somewhere, that Grignard plus formaldehyde, and this is the formaldehyde. If you use Grignard plus formaldehyde or organometallic with formaldehyde, you would get primary alcohol. This is the primary. If you add Grignard to aldehyde, how is aldehyde different from formaldehyde? Formaldehyde has 2 hydrogens attached, but aldehyde is 1 hydrogen attached and 1 R group. And this alkyl group, it can be methyl, it can be ethyl, propyl, whatever. Okay, so this is aldehyde. That's formaldehyde. Aldehyde already has 1 R group attached to it. So if you add Grignard plus aldehyde, you would get secondary. Okay? Plus formaldehyde, you would get primary alcohol. And Grignard plus ketone would give you tertiary alcohol. So if you have Grignard plus the formaldehyde, the resulting primary alcohol is going to have 1 additional carbon compared to number of carbon that was coming from Grignard. So for the Grignard, you have 1, 2, 3, and 4 carbon. Alcohol is going to have 5 carbon. Do you see the difference from reactant to product? Your product is going to have 5 carbon, is 1 additional carbon if you're adding formaldehyde. Where is that 1 carbon is coming from? It's coming from formaldehyde. You're not changing the functional group here. You're increasing the carbon chain in this type of reaction. So you would get primary alcohol. So this is the Grignard plus formaldehyde, and that gives you primary alcohol. Now, Grignard plus aldehyde, this is aldehyde. The R group and the R prime, the reason is marked as R prime because on the product side, you want to make sure that 1 alkyl group is coming from Grignard reaction and 1 alkyl group is coming from aldehyde. And the carbon that used to be CO double bond is going to be now COH. So COH or OH is attached to the same carbon that used to be double bond O. Okay. So when you bring the nucleophile, which is negatively charged, the nucleophile is going to attack the carbon. And when it does attack the carbon, the pi bond has to break over the oxygen because this carbon already has 4 bonds, needs to lose 1 bond, and the weakest one is the pi bond that will break. And then you get the pair of electrons on the oxygen, which is going to give you negative charge on the oxygen, or you have the alkoxide. Every time you add a Grignard reaction, you must follow by hydrolysis. So you have the Grignard added to the aldehyde, it gives you alkoxide. And then when you hydrolyze, it gives you secondary, it's a secondary alcohol. And why is secondary alcohol? Because the carbon that used to be CO double bond now is the COH. This carbon used to carry one alkyl group from the aldehyde, is gaining alkyl group from Grignard. So if the carbon is attached to two alkyl group and one hydrogen is a secondary carbon and the OH attached to secondary carbon is called secondary alcohol. What happens if you add Grignard to ketone? What would you get?
Get a secondary alcohol?
To ketone?
Tertiary alcohol.
Okay, what is the ketone? If you follow kind of the steps, you see what happens. You have ketone here. Whatever you add, this is going to change to OH, right? That will change to OH. You have your R and R from the ketone. So you have two alkyl group already attached to this carbon. You also have your RMGX, okay? RMGX, that this R group also is going to form bond with this carbon. So you actually have a R group here too. So if your ketone already has two R group attached to this carbon, Grignard is adding a third R group, then the carbon is attached to three other carbon is a tertiary. So Grignard plus ketone will give you tertiary alcohol. Grignard plus aldehyde will give you secondary alcohol. Okay, so for formation of tertiary alcohol, we have Grignard plus ketone, and then Grignard plus ketone would give us tertiary alcohol. So if you get a problem, to solve, to prepare this alcohol, the first thing you want to see, to classify your alcohol. What is this? Primary, secondary, or tertiary alcohol? What type of alcohol is this?
Tertiary.
It's a tertiary alcohol. So because it's a tertiary alcohol, and we learned that from Grignard, because it says Grignard or it doesn't say Grignard. We want to get it from like a Grignard, using Grignard reagent. So we want to have we see if there's other restrictions. Synthesize the following alcohol from compounds containing no more than 5 carbon atoms. If you want to start, no more than 5 is not going to work because this is a 7 carbon that we already have. So we have to ignore this part. Okay. So we look at these, we look at the alcohol is a tertiary alcohol. And because it's tertiary alcohol, then we say that it must be MGX, okay, RMGX, and plus CO double bond that has a R prime and R double prime, because it's a tertiary. Basically, it's Grignard plus ketone. If it's Grignard plus ketone, means that one of these 3 can come from the Grignard, the other 2 would come from ketone. Now you have the choice of bringing A, B from ketone, or AC from ketone, or AD from ketone, or AB, AC, or BC from ketone. It doesn't matter. 2 of them should come from ketone and 1 should come from Grignard reagent. So in this first proposal, there is using C, which is the ethyl group coming from Grignard. And if ethyl comes from Grignard, then methyl and cyclopentyl must come from ketone. So you have the CO double bond attached to methyl and cyclopentyl. If you choose A coming from Grignard, then B and C should come from ketone. That means to CO double bond, you should have a cyclopentyl attached and a ethyl group should be attached. So is there another choice? Can you have Grignard coming from the cyclopentyl? Yes, that's also another possibility. You have your Grignard coming from the cyclopentyl, and then methyl and ethyl would be part of the ketone. So you can choose either one of them. So the choice of having cyclopentyl Grignard and then methyl and ethyl part of the ketone. So you have three different choices because all you want to get is a tertiary alcohol. Okay, if you add Grignard to acid, chloride, and esters, these are known as the carboxylic acid derivative. Basically, if you have a carboxylic acid, when you put this, carboxylic acid looks like this, COOH. If you remove OH and you place Cl, that's like you get acid chloride. So this is known as the derivative of carboxylic acid. You add water to this, you hydrolyze, it's going to go back to carboxylic acid. So you can cleave this, leave Cl as soon as you add water. OH comes in and Cl would leave. Same thing here. If you hydrolyze it for ester, it can go back to carboxylic acid. That's why these two are known as carboxylic acid derivative. Each one separately. The first one is known as acid chloride, is coming from the acid, but instead of the OH, you have chlorine. So acid chloride. The second one is ester, which is a Fischer esterification, is coming from Fischer esterification, alcohol plus carboxylic acid. And you get this, and you learn about this reaction in organic too. But ester functional group is already known, and this is a carboxylic acid derivative. Now, if we bring the Grignard, okay, if you bring the Grignard, only 1 mole of Grignard, which is like a negative charge here and positive. So if this comes and forms bond with this carbon, what would happen next? What are the choices? What should happen?
The pi bond will break on the oxygen.
Is that the only choice we have? That's a good answer, but what's the other choice?
You have the leaving group on the chloride.
We have a leaving group, right? Yeah. So for the first one that comes in, the leaving group is going to leave. So if R adds here and leaving group leaves, what do you have? You're going to have CO, R prime, and then R, right? This is what you're going to get. Because the first, I was talking about the first Grignard reagent, when it comes in, since you have a leaving group, would leave and it's going to give you a ketone. But since in the reaction mixture, ketone forms, you cannot isolate it because it's mixed with Grignard reagent. And we saw already what happens when you have Grignard and ketone in one container. What's going to happen? The second mole of this is going to attack the carbonyl group. Now you don't have leaving group. Now what happens? This is the second mole. I'm just going to say second mole of the Grignard will attack the ketone that was formed from the first mole. So this is the first mole. Would give you Grignard. The second one, the second mole comes in, and now you don't have leaving group. In this case, pi bond will break over the oxygen. And when it breaks over the oxygen, you protonate, you get the OH, but you are adding 2 R groups to this carbonyl group. You already have one, you're adding two more, it's going to make it tertiary. So Grignard, or 2 moles of Grignard plus acid chloride would give you tertiary as well. Same thing for ester. When the first Grignard comes in, OR is not the best leaving group, but it is leaving group. It's not hydrogen, it's not R group, or is not oxygen by itself. It's OR. Your protonate is like alcohol, so it can leave. So when the R group comes in, the first mole, this is going to leave. OR would leave. And kind of similar to this is going to give you ketone. And then second mole of Grignard with the ketone would give you tertiary. So acid chloride and esters with ketone with 2 equivalent of the Grignard would give you tertiary alcohol. The first equivalent will add to carbonyl group and produce ketone, and the second equivalent of Grignard would add to ketone and it gives you tertiary alcohol.
Professor, in the example with the ester, where are the R groups in the tertiary alcohol? There's 2 of them from the ester, or is that 2 moles of the
2 moles of, okay, good question, very good question, because that's how you know that this is what actually was coming from ketone or was coming from acid chloride or this, because the 2 R groups that are coming from Grignard is going to be identical. So if you have 2 of the R groups that are identical, you can use this method to prepare it. Because when you use acid chloride, 2 R groups come from Grignard and they are identical. If you bring like a methyl Grignard, then both of them is going to be CH3. So 2 groups are coming from Grignard and 1 is coming from either ester or from acid chloride.
Okay, and the O stays attached to the carbon, right? Just the R group leaves, and a hydrogen takes its place.
No.
Oh,
See,
the whole OH leaves.
OR would leave here. OR would leave.
OR
and
leaves, I mean,
changes
yeah.
to ketone. Yes, OR would leave, and this changes to ketone, and then the second mole that comes in would break the pi bond over the oxygen. This oxygen is the one that I would show here, not this one. The oxygen
Okay, I
that
see.
we have on the alcohol is coming from carbonyl group. The CO double bond would always change to COH. This is the used to be CO double bond.
Gotcha.
Used to be CO double bond. Very good. So if you look at the mechanism for this reaction, I'm more concerned about the steps of what is happening, because you could say the pi bond breaks and it comes back and then makes the Cl leave, and then some books they represent this as like R comes in and the Cl would leave, so you end up with ketone. So you can just say that the first mole of the Grignard with acid chloride is going to give you ketone. Then the second mole of the Grignard with ketone, it gives you tertiary alcohol. Basically gives alkoxide and it's going to change your protonate and changes to tertiary alcohol. Okay, so far, what you have learned so far for the Grignard reactions are MgX plus formaldehyde. It gives primary alcohol. RMgX plus aldehyde gives secondary. RMGX plus ketone that gives tertiary. RMGX plus acid chloride would give you tertiary. Just have to make sure that you're using 2 moles of the R group. And same thing for ester. So you have 3 different methods that you could make actually tertiary. You have only one way to make secondary, that's the RMGX or Grignard plus aldehyde that gives you secondary. Of course, you can make secondary alcohol by reduction of ketone, but with the Grignard, this is the only way, RMGX plus aldehyde. For primary, you have 2 methods. RMGX plus aldehyde would give you primary. Also, RMGX plus epoxide would give you primary alcohol. Okay. You need to memorize all this. I mean, there's really no other way other than memorizing. Okay, so number of carbon is going to be R plus 1. Primary alcohol number of carbon equals R plus 1. So whatever number of carbon comes from R, you add 1. In here, number of carbon equals R plus 2. So addition of 2 carbon, 1 and 2. 2 carbon would be added to the R in the product. Questions? Please make sure to take some notes to yourself, prepare flashcards and write, you don't have to put the general formula for it. You just say formaldehyde instead of saying here CO double bond attached to hydrogen. Here is aldehyde, ketone, acid chloride, and ester.
Professor, would you mind going through the equation for the top one?
The
triangle?
No,
Yeah.
it's actually is coming. I kind of, yes, addition to
Jump
the
the gun a bit.
oxide, definitely, yes. It has to be ethylene oxide, okay? Has to be ethylene oxide. That means there should be no other alkyl group attached to these carbons. They must be hydrogen, the other 2. So it's basically ethylene oxide or epoxide. You see that R is a negatively charged here. Mg is positive, so it's acting as a nucleophile. It can come and form bond with one of these carbons, okay? Then you have a triangle here. Let me use a clear, a better slide there. But you have a triangle, and if you have a triangle, you learn that in chapter 3 is 60 degree, is forced to have 60 degree, and it's putting a lot of pressure in this compound now. So as soon as you bring the R group to form bond with one of these carbons, the weakest bond is going to break. So this bond, which is pair of electron, would move over the oxygen and it gives negative charge. Then you protonate and you get OH. And it's going to be on the first carbon because it doesn't matter which of these is being attacked, the oxygen will break over the other carbon. So let me show you on a more clean slide here. Addition to the ethylene oxide. the nucleophile or the R group from the RMGX, basically we've been looking at it like this. Okay, so this carbon with the negative charge, it would attach to one of these CH2s. And when you say ethylene oxide, that means you do have 2 hydrogen on each of these carbons. The bond will break over the oxygen. You have alkoxide, and then you protonate. Every time you add Grignard, you must follow by hydrolysis, and you get primary alcohol. This primary alcohol has R plus 2 carbon, 2 additional carbon, and is going to be primary alcohol. This is an example with the alkyl group, a specific alkyl group for the Grignard, but ethylene oxide doesn't change. So ethylene oxide is the same, and the oxygen is going to break over the last carbon, and that's why you get a primary alcohol. Questions? Did they answer your question about the?
Yes, yes.
Perfect. Any other questions? So we see a lot of good stuff about the Grignard reactions. You can make Grignard from any type of halide. It could be alkyl halide, aryl halide, allyl halide, cycloalkyl halide, and all types. And you can make primary, secondary, and tertiary alcohol many ways, in different ways to make tertiary, at least like 3 different ways, for primary 2 different ways, and then for secondary also one way to make secondary is the Grignard plus aldehyde. But there are some limitations for the Grignard. Grignard, you cannot make it from compounds that they already have OH, NH, or SH. Basically, these are going to destroy the Grignard reactions, or terminal alkynes, because it's going to destroy the Grignard. Since it's going to destroy the Grignard, you cannot use Grignard with this compound. So any acidic protons cannot be included in the molecule, because just like water is going to get it's going to gain hydrogen and it changes to alkane, and OH would be replacing this R group here. You get XMgOH, and this is like a precipitate. It is unreactive. So you start with a reactive reagent, which you need for this reaction. But if you expose the water or any acidic hydrogen, it can go to alkane, and alkane is not going to give you alcohol. Ethyl lithium as well, like lithium, alkyl lithiums also, they are not stable around water because it changes to alkane and then lithium hydroxide. Here you have like the magnesium gaining hydroxide, same thing here. So this is one of the limitations, and is a major one, because you cannot work or make Grignard with the alcohol or thiols and others. Questions? Okay, another method to prepare alcohol is reduction of carbonyl. Remember, oxidation of the reduction of aldehyde would give you primary alcohol. Remember about the definition for oxidation and reduction in organic chemistry. Reduction meaning adding 2 hydrogens, okay? Reduction meaning adding 2 hydrogens. Oxidation means removing 2 hydrogen or adding oxygen. Okay. So the reagent for oxidation and reduction, you need reagent. Oxidation, permanganate was oxidizing agent because it was adding oxygen. Remember, permanganate plus alkene, it adds like OHs. Hydrogen peroxide is oxidizing agent. Silver oxide is oxidizing agent. And then for reduction, you must bring something that can add hydrogen. So we are adding like sodium borohydride, and hydride meaning H minus. Okay, hydride is like a hydrogen with pair of electron that is going to have negative charge. And because of this, it can act as a nucleophile. Because of the negative charge and pair of electron, it can act as a nucleophile. So it can add to any positively charged carbon. So if you have a carbonyl compound, same thing for lithium aluminum hydride, because it's hydride again, that means it contains H minus, 4 H minuses. This one contains for like 4 H minuses. And they are going to act as a nucleophile and attack the CO double bond. Ranitol with hydrogen. So it's not just the ranitol. Nickel by itself is not reducing agent, but if you add H2 with the ranitol, it's going to be adding hydrogen to it breaks the pi bond and adds hydrogen. You can saturate it basically. So if you have aldehyde, let's see if the next slide has example, or I come back and I write the example here. So sodium borohydride and aluminum hydride, lithium aluminum hydride, they are both sources of hydride ions. So hydride attacks the carbonyl, just like nucleophile of Grignard. Hydride would attack the carbonyl. There is no leaving group here. We said alkyl group and aryl group. These are not good leaving groups. Oxygen is not a leaving group. So pi bond will break over the oxygen, and you have added a hydrogen. One hydrogen already is coming from hydride. You hydrolyze this or add water, add hydrogen, protonate is going to change to alcohol. So you add one hydrogen from hydride, another hydrogen from the solvent, and you protonate, you get alcohol. If it's a ketone, it will give you secondary alcohol. Okay, if it's a ketone. If it's aldehyde, it will give you primary, but the mechanism is exact same. So sodium borohydride contains hydride ion. Hydride acts as a nucleophile, is going to attack partially positive carbon that we have here. Okay, and whenever nucleophile attacks a carbonyl group, there are two cases. If there is leaving group would leave. If there is no leaving group, pi bond will break over the oxygen. So you get the alkoxide, and when you get the alkoxide, you protonate that, you get alcohol. Now, if it's a ketone, this carbonyl group that now is changing to COH already has two groups attached to it, so it's going to be secondary. If it's aldehyde, it would be primary. Okay. Questions? Lithium aluminum hydride, it works the same. Lithium aluminum hydride is stronger than sodium borohydride. Lithium aluminum hydride, it can reduce aldehyde. So if you have aldehyde and you add LAH, or this is the abbreviation for lithium aluminum hydride, it would change to primary alcohol. Lithium aluminum hydride, if you have ketone, it would change to secondary alcohol. It's strong enough that can also reduce the carboxylic acid and acid derivatives like ester that we have here. So if you add LAH, it would change to primary alcohol. So with the reduction, you can get primary, secondary, but you cannot get tertiary. You can get either primary or secondary. So the comparison of lithium borohydride with lithium aluminum hydride and sodium borohydride. Sodium borohydride can only reduce aldehydes and ketones, and it is a weaker reducing agent, but lithium aluminum hydride is a stronger reducing agent, and it will reduce both aldehyde and ketone and carboxylic acid derivatives. So lithium aluminum hydride can reduce the aldehyde to primary alcohol and also carboxylic acid derivative to primary alcohol. Sodium borohydride can reduce aldehyde to primary alcohol, ketone to secondary alcohol, and cannot reduce the carboxylic acid or ester or acid chloride. So let's follow along with this example. What type of functional group we have here? Ketone, aldehyde, carboxylic acid, ester, acid chloride. What do we have?
Aldehyde.
Aldehyde plus sodium borohydride, which is reducing agent. The product is, what's the product?
Tertiary
What type
alcohol.
of product? What type of product? Aldehyde would go to primary. What does primary alcohol means? It means that carbon is attached to only one other carbon. And because aldehyde is at the beginning of the chain, that can help you with this, determining that if it's aldehyde, it would most likely go to primary alcohol, right? And second one, just follow along the example. What do we have here? 2-butanone, what is that? Aldehyde, ketone, carboxylic acid, ester. What do we have here?
Ketone.
We have a ketone. Ketone plus your reducing agent is sodium borohydride. And the product is, what's the product?
Primary.
Secondary alcohol.
Secondary alcohol. Okay, ketone is attached, a CO double bond is attached to 2R group or is attached to 2 carbon. So this carbon is a secondary carbon, and this carbon is going to remain secondary carbon because we are not changing the alkyl groups here or number of alkyl groups. All we are doing, we are adding 2 hydrogen, 1 hydrogen to the oxygen and 1 hydrogen to this carbon. We are not changing the number of alkyl group. If we have 2 alkyl group on the reactant side, we are going to have 2 alkyl group on the product side attached to this carbon, and it makes this carbon a secondary. And if it's a secondary, then the alcohol is going to be secondary. Okay, following along this next example, what are the different functional groups that we have here? We have 2 functional groups. This one is ketone, aldehyde, carboxylic acid, ketone. So we have a ketone here. And this side, what do we have here? Ester, right? That's the ester functional group. We have ketone and ester We are adding sodium borohydride. What do we get on the product side?
Is it primary?
If we have ketone would give us what? So if it's the same thing, okay, ketone here, it gives you secondary, ketone here has to give secondary also. If it's ketone, you reduce it, it will give you secondary. So we get secondary alcohol. Why secondary? This is a carbon, is attached to two other carbons. That's why secondary. Or because it's ketone, you reduce ketone, it will give you secondary. You reduce aldehyde, would give you primary. So what happens to ester on the product side? It remains. Why sodium borohydride does not reduce ester?
You don't have a good leaving group?
Sodium borohydride is
Weak nucleophile?
weak reducing agent, is not a strong reducing agent. Sodium borohydride is weak reducing agent. And if it's weak, it can only reduce aldehyde and ketones, cannot reduce ester or acid chloride or carboxylic acid. It can only reduce ketone or aldehyde. That's why if you put sodium borohydride, and this is a question on the quiz and exam also, if you put sodium borohydride, you have to be careful. You cannot reduce everything. If you had this, let's say you had a compound with the ketone functional group and you had aldehyde functional group and you add sodium borohydride, what would be the product? Which ones would be reduced?
Both of them.
Both of them, because sodium borohydride can reduce ketone to secondary, and it can reduce aldehyde to primary.
So it just can't reduce esters.
Sodium borohydride is weak, is not strong enough to reduce ester. Yes, that's right. So you have aldehyde changing to primary, ketone would change to secondary. So let's follow along the next example. What are the functional group that we have on the last example on this slide? We have two functional group. One is
Ketone,
ketone. So we have ketone. And the other one is
ester.
ester. We are using lithium aluminum hydride. What happens to ketone?
Ketone gets reduced.
It gets reduced to secondary
Secondary alcohol.
alcohol, and ester would be reduced to primary.
Primary.
So we learned that esters would be reduced to primary. Ester does not get reduced to secondary. If you have ester or acid chloride, it will reduce to primary.
Professor, how do we know if they're like strong or weak reducing agents, or if they're oxidating agents? How do we know that? Or do we need to memorize it?
Okay, the magic trick was to memorize it. And how do we know? It's from this slide number 40 that sodium borohydride is weak because it can only reduce aldehydes and ketone, but lithium aluminum hydride is strong because it can reduce everything. Aldehyde and ketones in this diagram, they are on top, upper, and it's this green line, it shows ease of reduction. What does it mean? That means is that the aldehydes are the easiest to reduce, then is ketone, then is ester and the acid anion or carboxylate ion. If lithium aluminum hydride can reduce ester, it would definitely could reduce aldehyde and ketone, right? Because these two are easier to reduce.
But it can't do it the opposite way around.
It cannot, yes. But sodium borohydride cannot reduce ester or the acid anion because it's weak, it's not strong.
What makes the sodium weaker than the lithium?
It's just I guess it's just the nature of it. I can give hydrogens. It can give like more hydrogens.
Well, I'm
than
saying, I'm asking because are these the only reducing agents we're going to be exposed to on the test and quiz and stuff?
Oh, three of them. Okay.
There's a third.
It was the third one was the hydrogen. It was for hydrogenation. If you remember, it says Ran nickel. So it's the hydrogen with the nickel or platinum or palladium. So you have three reducing agents to worry about.
I see.
Strong, weak, and this one is strong, but is used for saturation as well. So this can reduce aldehyde, okay, double bonds, ketone, and aldehyde.
So that one's similar to the sodium.
With one exception. The exception is that the sodium borohydride does not reduce CC double bond, but H2 reduces the CC double bond.
Okay.
Yes. So yeah, you have to memorize the reducing agents because you want to use the reduction as a preparation of the alcohol. So you need to know your reagents. What are the agents that I can bring to aldehyde or ketone, and then to change them to alcohol. Okay, we looked at those examples. Let's look at next. Okay, for the catalytic hydrogenations, this is basically hydrogen with the Ran nickel. That's the third reducing agent. And this can reduce both of these. Now, if you were going to use sodium borohydride, know the difference because you see this question on the exam. If you were using sodium borohydride, the CC double bond would maintain, but aldehyde would change to primary alcohol. So in this case, you have primary alcohol and the CC double bond also got saturated. So these two take it to different route reduction. And the reason for this different route is that your reducing agents are different. If it's catalyzed by, if it's hydrogen catalyzed by Ran nickel, it can saturate the pi bonds as well, from alkene and alkyne all the way to alkane. But when you are using sodium borohydride, because this is only attacking the carbonyl group, so you must have that, the positively charged carbon. So it will reduce the aldehyde and ketone, but does not reduce the CC double bond. Very good. Questions?
So on that last one, can you use two reducing agents at the same time in a reaction?
No, you use one or the other.
Okay, so that one is just showing what we would see with either or.
Yes.
Yeah, just for
Not like-
comparisons.
Yes,
Okay.
either or. If you use the H2 with the nickel, what your product will not maintain the CC double bond, but if you use sodium borohydride, it will maintain the CC double bond. So the point is what you are supposed to do. What's the aim? Are you going to keep it or saturate? Okay, so preparation of the alcohols. You have hydration methods that you had, and then you had the diols. They were all covered in chapter 8. The organometallic compounds or reagents, they were covered in this chapter. So these are new. If they attack the CO double bond, carbonyl group, you have to look at the carbonyl group if it contains any leaving group or not. If there is a leaving group, the leaving group would leave. If there is no leaving group, the pi bond will break over the oxygen. And then you protonate that, and that changes to OH. You could also do reduction of aldehydes, ketones, or acid derivatives in order to prepare alcohols. And for that, you need to know the reagents that are known as reducing agent, strong or weak reducing agent. So we have 3. There was one slide that actually mentioned about 3 reducing agents. So if you go back and look at slides again, or the video, watch the video, you would see that there's a slide that introduces first what are the reducing agents, then uses for the reaction. Okay. Last part of this chapter mentions about the thiols or mercaptans. In the Y under alcohol, you have to talk about thiols because oxygen and sulfur, they are in the same group of the periodic table. So if OH, it gives alcohol, SH gives thiol. So basically is the OH attached to carbon from the alkyl group, and have to make thiols. To make thiols, you have to do substitution reaction from alkyl halides, and you have to bring a nucleophile. In substitution reaction, you have leaving group, which is in alkyl halide, you do have leaving group, and you have to provide the nucleophile. The nucleophile that is used is the HS minus, and in order to keep the HS minus, should be in the ionic form to make the nucleophile available. So you cannot bring H2S because it's a weak acid. So it's not going to give enough of the HS minus. But if you bring Na plus HS minus, sodium bisulfide is going to, or sodium hydrosulfide or sodium hydrogen sulfide, few names, you learned that from general chemistry. So HS minus is more available as a nucleophile, and it can attack the alkyl halide. Leaving group would leave, replacement or substitution reaction would give you a thiol as a product. Any rule that applies to SN2 reactions, it will apply here. You do need a strong nucleophile and you need a good leaving group. This is one of the examples that is used in the oxidation reduction in proteins. Mercaptans, those you have to be able, they are used to reduce proteins and denature protein. I used them for 5 years in a research that I needed. They smelled very bad, and none of my group members, they liked me those days that I was using mercaptan. And if I went, it was like a mark that left in the lab. It says, oh, maybe the mercaptan was used today. So they knew about it. And they don't smell good at all. But it denatures the protein. If you want to do anything, research on the protein, you have to first denature it and change it from the coil to the primary structure of the protein before you can study the protein. So it's used as a reducing. Okay. So if you oxidize, basically you're removing the 2 hydrogen. When you reduce, you're adding the 2 hydrogen. Any questions? We're done with chapter 10. Do you have any questions? What you will learn in chapter 11 is going to be about reactions that could happen to alcohols. Basically, you start with alcohol, what would be the product? You can do dehydration of alcohol to get to alkene. You can oxidize a secondary alcohol to go to ketone. You can oxidize primary alcohol to go to aldehyde. You can do substitution. And if you have alcohol and you add PBr3, you end up with alkyl bromide. So you end up with alkyl halide. You can reduce to alkane. How could you reduce alcohol to alkane? To reduce alcohol to alkane, first you have to do, let's say you have OH here. There is no reducing agent that would directly take this to alkane. So what you have to do, so this is not possible directly. So what you have to do first, you have to dehydrate this and change to alkene, then add H2 in order to change to alkane. So it's like indirectly. Another method you could do, you can tosylate. I don't know, we talked about tosylation, but it comes in chapter 11. You have to tosylate it first. So you have to change that to OTS. And then you can use LAH or sodium borohydride to replace this with hydrogen, and it goes to alkane. You will learn that in organic too. So you can, but you can reduce, you cannot reduce directly. Since we talked about reduction, we cannot, there is no reagent that can reduce alcohol to alkane directly. You can do differently. You have to do 2 other steps. Extra steps. Esterification, acid plus alcohol, it gives you ester. Tosylation, so that's the reaction that you would learn. And synthesis of ethers, if like dehydration of the alcohol can give you ether. Or if you're using the Williamson synthesis, it would be alkyl halide plus the alkoxide. Questions? Any questions for me?
So for the chapter 11 quiz, do we just?
There is no chapter 11 quiz. Let me stop recording, please. Pause it.